it doesn't work, you can maybe check, and now it's working again, or okay. So let's see how long it works. Otherwise, maybe if it doesn't work for a long time, you can ask, maybe ask, write to Carlos if he has an idea, just debug it. Okay, let's see if I also see now. I also see now something. It's good. Okay, so welcome to the lecture Deep Learning and Neural Networks. My name is Janius. I'm here leading the AI for Language Technologies labs. And yeah, this time, for the first time, this course will be organized by me. So it will be a bit of a different lecture than the previous years. Which maybe is good, maybe also leads to some start of hiccups. So I hope you can forgive me them. And I'm looking forward to this lecture. I hope you're all already a bit fascinated about what is possible with deep learning and with neural networks. And that will be the main topic of this lecture. So we want to look into yeah, what is the core of current AI systems? How does it work? And to get a hopefully deeper understanding of that. For that, we will start today with a bit of motivation, where all this technology is used. Then we have to do a bit of this boring organization stuff, but I guess it's good to know. And the main two content-wise things what we'll cover today is we'll give a brief history of how neural networks and AI have developed, and then we'll do a repetition on what you hopefully have know already a bit. Although this is the course of neural networks, by now I think neural networks are all over your curriculum. So you have, I guess, been in touch with a bit of neural networks before, and we'll try to, yeah, wake this up. We'll repeat a bit what is the basic of the feed forward. For the ones who have yesterday been in AI2, I don't know who's listening to AI2. Okay, so the last part is a bit of repetition for you. It's mainly a similar repetition of what are basic neural networks and what is the concept there. I hope it's good for you to hear the twice one. Don't worry, that's not the normal thing. You'll not have a lot of overlap in this, but the neural networks are just, yeah, so core to both, of course, that I think it's good to have a good starting basis in the first lecture. So why should you worry about, or why should you care about neural networks, and why is it important? if we look at what current AI systems are, the core backbone of all of them is our neural networks. One example is here the ChatGPT. I guess a lot of you have used it in some way or another. And the main idea behind that is that there is a large neural network which does this prediction, what is the best answer to the user's input. It's one type of neural network, which we'll look into, these new large language models, the foundation models, which are, surprisingly good in doing a lot of these tasks. It's not only ChatGPT, I guess you followed the news, there's a lot of others, Claude and open source variants. So we'll cover that at the end of the lecture, because of course you should, I mean, in a basic deep learning and neural network lecture, we'll start with more basic architectures, but the hope is that you have a more grounded understanding of how these networks work. But there's even more coming up. Recently, I guess some months ago, a lot of you have seen this demo, which is Sora. It's also by OpenAI. So in this case, it's like a video generation thing. So you start with a prompt, you tell it what the video should look like. And now this video is not created by a human, it's not recorded. That's all just generated artificially. So you just describe what you want to have, and creating video content is a lot easier now with AI tools. Of course, there is still a lot of open issues and not everything works fine. But I think it's surprising when you see how good this works when you compare how maybe similar things were happening only a very few years ago. So there is a real large progress in this area, and we want to look in this lecture like what type of models and architectures are used in there. Also in other areas, we are seeing the use of neural networks. We, of course, will not cover robotics. There's a lot of very good robotics lectures at KIT, but also in robotic applications, neural networks are nowadays really an essential one. So this is the SeiCan demo, which is also mainly a large language model at the background, which predicts and does the planning. And that is mainly the very interesting thing about neural networks, that really some years ago there was really very dedicated solutions for all of these, and there is like a whole research field where each one is only focusing on one particular application. The interesting thing of neural networks is that they are nowadays the core basic component in all of them. So we can in all of them use them to achieve this type of performance. Of course, there's a lot more at the end, so it's not purely you can train a neural network and that works. There's a lot of around that, how you prepare your data, how you apply it, how you train that. We will look at that, but then of course there comes in also domain knowledge about the current thing. That will not be the core of this course. It's more about how you build the neural networks, which are the backbone, and then how you apply the domain knowledge you can get in other lectures from our sites, for example, in natural language processing in the winter, or in vision, or in robotics or so. Another use case which we're also using here at KIT, and a lot of you, I guess, have seen it, we're having the lecture translation system, which hopefully is currently running. And this is also just running by large neural networks. There are different components behind that using neural networks, which do then something like text to speech. So you transcribe what I'm saying, or you translate it in many other languages. And behind that, there's again a lot of neural networks by now. So each of these components are by itself a large neural network. And with this, I hope you can see that there's really a large variety of different applications where by now there are some neural networks in the background. You can follow lectures in different languages. You can control robots. A lot of prediction tools in both finance and climate are using this type of neural networks, and therefore it's really essential to understand this technology. Let me see if I can. There's also other tools which you're using nowadays. If you think of Siri or Amazon Alexa, again, behind this is our other speech and language tools. Behind them, you'll see a lot of these neural networks in there, and they are really, essential to build any type of AI component at the moment. It's a bit, of course, they're hype at the moment, and maybe at some point people will develop other solutions. But currently, you really see that in nearly all AI fields, when you talk about AI, you're meaning that you're using deep learning and a neural network to solve the task. And this is just because recently, at the moment, there is no other technology which you can use to achieve similar performance in these use cases. So in all of these, if you think about it, there is some type of perception. So you have the world, you want to generate something, and in between, you're always using this type of neural network to do these tasks. So in the neural networks, how we see everything is we have some type of input. We need to like somehow encode this input, and we'll look into how we best encode that. And then the neural network is mainly like some type of function that we have to learn, which takes this input and generates something here. That can be more easy task, what we'll look into today, where we have like a fixed like vector representation, and we're generating another vector representation. And these vectors are, of course, very generic, but then you can have tools, or you have to think about how can you display your world or what you see really as a vector image or as a vector representation, and how you can understand that. And we'll also look, of course, into more complex decisions. Then often you don't do one prediction. If you're thinking about the previous one where you do text processing, you're not taking one neural network, doing once a prediction is done, but typically you're doing prediction by prediction. So you maybe need more complex neural network structures, but the basic idea is always in the middle, we have this type of function which does it. So what is a neural network? It's really mainly a machine learning model. It is originally inspired by biological neural networks, so what we have in our brains. However, what we see currently, or what we are seeing now, is often not that strongly connected. That, and it's not like or maybe sadly, it's not like, oh, you have a good idea how the human brain works, and then you transfer that and similar performance. There are often other conditions that are more important to get good performance. So these models are nowadays often, for example, designed by working very well on your hardware architecture. So how can you have a neural network design that is just computational, very efficient? That is often at the moment a more important target than to make it somehow more brain-like. It might change at some point, I'm not saying that, but it's just like today, when we look at the different architectures, they are often inspired by how can we make it an efficient computation so that we can just process as much data as possible through that. And we'll have different structures, but one important thing you see here already is these types of layers. So the basic idea of neural networks is that we have some input and we process it to the next layer with quite simple operations. So each of these operations are typically always very, very simple operations. And then at the end, and we do that layer-wise, where there's only interactions between the different layers. The very important thing is that this is not designed by hand. It's everything, it's machine learning. So we're trying to automatically infer the parameters of the model from some data. If you think about it, the ChatGPT thinks it's like billions or trillions of parameters. So that's not possible. You cannot like start coding and say, oh, this weight is 0.5 and this weight is 0.6 or so. But we have to learn that and learn how to do that. And we are normally approximating some function from input to output. And that is the whole goal of the learning. When we're talking about deep learning, not really like a super specific term, but it was more coined in the 2010s or so, where these people got bigger and bigger. We talked about the layers already. So if we are having a lot of layers on top of each other, then people are talking about the deep learning, because these networks get deeper and deeper. And if you look at current models, they go up to like 100 layers or so. So, but in the end, it's not something different. It's still a neural network. It's just want to highlight that, yeah, the way of doing it is by having a lot of different layers. Good. So this is somehow a bit of a motivation for why I think this is a super exciting topic and why you should follow the lecture. And with this, we will then now first do some of the organizational things, and then we'll look into that. This is quite a long, has already a long history. People are working on it for 80 years already. And then again, repeat the basics, which I just started already a bit. Just again, so as I said, the main, I'll be the main lecturer, so the most of the lectures will be given by me, but I'll have support by Tu-An, who is sitting here in front, and she will organize the practical parts. So again, this lecture will have both lectures where you're directly listening to me, hopefully interacting with me and asking questions. So if there's anything unclear, please always ask. It's a lot more helpful if you ask the questions you have, because most probably some of your other students will have the same questions. But then it's also important that you're not just listening to it and trying to learn it. To really understand it, you have to do it yourself. And therefore, we'll have 6 practicals in there where you should encode yourself these type of neural networks, because hopefully after the lecture, you're not going out and saying, oh God, I didn't understand anything, but you're saying, oh yeah, that's now very clear. I know what a neural network is, or this type of neural network. But often if you then have to do it yourself, you'll see things which you haven't thought of and which are unclear. And therefore, it's really essential that you really build these systems yourself. So as I said at the beginning, what we want to do today is doing the organizational information, then having a look at what is the history of neural networks, and later like go back to the basics of neural networks. The first thing is, of course, what do we cover? So here's a rough schedule of what we will cover. You see in purple, there's like 6 practical things in there. You in yellow have sometimes off. You have some holidays. That's, of course, also good. From the topic-wise, we start with some type of introduction. Maybe surprisingly, already on Thursday, we are doing a bit of an excursion. The success of neural network is heavily also due to the fact that we can do very good computation, and that it really boosted it in the 2010s. And that is because we're using no longer general CPUs for it, but we can do it on on GPUs. And that is really a co-designing effect. So then people also started to develop neural networks which really work well on GPU. And therefore, it's essential to understand a bit of like how calculation on GPUs is done. And that we'll do as a very brief excursion on Tuesday and on Thursday, so that you understand later if there are some decisions why people use this model or that may be partly because it's just working better on a GPU, or it's easier to. So it's good to keep some of this in mind, and we'll do this very brief introduction. Also, we'll explain that a lot of the things we have today we don't have to do anymore. The backpropagation algorithm and the calculation of the derivation can nowadays all done automatically, and you'll see that with things like the current software frameworks. You mainly design your network, and then how to do the training is done automatically, and we'll get a bit into that. Then the first part of the lecture till around mid-May will be about different architectures. So what are the different network structures that we have? What are the different architectures? I assume you have heard about some of them in previous lecture. Who has known about convolutional neural networks? Or yes, so we'll only cover that partly. And recurrent neural networks. Yeah, okay. So you see that we'll do as one together, like a more deep dive repetition to that, but then we'll also cover other things like transformer, self-attention, like state space models, and so on. Then the second part is about training. So how to train these networks, basic training, deep learning, deep networks training, what are the tricks, how to do transfer learning, and so on. And at the end, we'll talk then a bit about what is currently a lot hyped, these foundation models, which you can use to then transfer the data, to transfer your knowledge to other tasks and be really very good. We'll also have some invited lectures here by different presenters who will show you their view on neural networks. In addition, we have the practical sessions. So the practical sessions are not created. They're really just for you, but I can only advise you to really do the practicals. Normally, you really get a deeper understanding, which will also help you in the exams. Of course, the style is a bit different. We will have them, you will do real programming there. So you'll learn how to really use the code, while of course in an exam we can't ask you to write large Python programs, but still there is a large benefit, and I can only advise you to do that. We will try to give you the exercises around 1 week before the practical, then you can work on them yourself, and then we will discuss the solutions with you in the practical sessions. There's of course also infrastructure. We'll try to put all information always on Ilias. You should see there already the current slides. We'll try to put there always the current slides. Might not be super early. I'm also, like I assume, several of you more working towards deadlines, so I'm not done like 3 weeks in advance, but you should be able to see all your slides there. We'll also record these lectures, so if you're not possible to come here in person, you can download them from the archive on the lecture translator. I still advise you heavily again to join the lecture and not just watch 1 week before the exam all the videos. That's normally not working really well, but you're old enough, so it's of course your decision. With this, we are coming to the last part. I guess you're also interested in how to write the exam. So the exam is fixed already. It's in September on the 18th from 2 to 4. I mean, the exam itself will be a 60-minute exam. It is, of course, then in the 2 hours with preparation and so on. It's a normal pen and paper exam. Of course, since the course has changed, the content has changed. The content might be a bit different than previous exams, but it's still neural network, so it's not a complete different type of exam. And from the content wise, as I said, we have the 3 main blocks we'll look into. We'll start with after this week, we'll start with architectures. Then we'll having several lectures about how to do learning, how to train the models. And there, of course, I mean, the basic learning and the backpropagation we'll cover already today, and you have done, but there's a lot of ways around it, how to really make it work, that we'll cover there. And then we'll look a bit at foundation models at the end of the lecture. Good. So Any more questions on organization before we are looking at the history? Yeah. I guess you can try it. I mean, you don't have to submit it. So if you take the task, you can try to implement it in TensorFlow. But if we provide partial input, that will be just in PyTorch. So things are normally easier. I would advise you maybe to use it because it's easier to learn. I guess if you know TensorFlow, it's not too difficult to use to learn the other things than like to implement everything around it. But I mean, as we don't control, as we are not correcting, you're of course free to solve the problems in any toolkit you like to. If it's too crazy, it might be that we can't give you a lot of feedback on it, but that's really up to you. Good. So with this, let's have a look at how neural networks and AI has evolved over the years. So maybe we start with the neural networks, and you see first type of these neural networks where have quite a long history. So we have seen these in 1943, McCulloch and Petz, they have like the early model of a neuron. So the main idea was just you take the weights, the vector product of the weights and your input, and if it's larger than 1, then it's the 1, and if it's lower than 1, then it's -1. So this is really the basic perceptron. We'll come to that later. It's what is still there in a lot of in all neural networks at the moment. The important thing is this: there was at the beginning there was not yet really a procedure of how to learn that. So this was just a model where you mainly had to define your weights yourself. So there was no learning in there, but this was a relative powerful model which could more do than just an AND, an OR, or an OR on your type of input gates. So you see, we're like having of more than 80 years of somehow initial research on that. When you think of that, oh, this is the newest technology we have, it's maybe good to keep that in mind. There has been quite a lot of initial work on that. Then there is the first algorithm which tries to learn these types of weights. It's the so-called Rosenblatt perceptron, which learns your weights by a loss function already. It's not doing backpropagation. You see, you directly learn your weights in this way. But it was the first algorithm where you can learn a model which tries to do this prediction. Thereby, of course, there is a first hype around it, and people were like quite interested in that, and you could see. Then, as you'll see with neural networks, there's often this summer and winter people talk. There is a hype, and then afterwards, people recognize it's not working that well. Does anybody know what is the problem of this type of perceptron, or why it wasn't that successful at the beginning? Yeah. Yes, so that was just like 7 years later, people found out that we'll again look into that a bit more in detail, but that a very simple problem, the XOR problem. So you have two inputs, and the output should be XOR of the inputs. So if both are 1 or both are 0, the output should be 0, and if one is 0 and the other is 1, the output should be 1. So very simple problem, but your Rosenblatt perceptron cannot solve this problem. So it's not possible to build a model which can do that. Which, of course, is a bit discouraging, because if you can't solve these quite simple type of function, you might be skeptical that you can really build really huge models out of that. So this wasn't that successful yet. However, there is further research also after this winter, and there is a Fukushima neocognitron, which is already then a multi-layer perceptron, which can do some type of recognition. So this already, at least from the image, looks already a lot more when you've seen current neural networks. That looks already a lot more as what we are currently using. So you see there is still progress. People are able to, just by replacing a single neuron by this layered structure, which is essential for neural networks. We are talking about a lot about architecture, so how to stack things and make them possible to do this type of processing. We see that it's possible to really build larger models. Then there is one additional important step, is to do the backpropagation. So that's really basic math, but it's essential that we can learn the weights in each layer by like calculating how big the contribution of each weight to the error is. And that makes it possible to do gradient descent and then do an efficient search for a good solution for good weights. This backpropagation for neural networks was introduced in 1982. There has been several works on general optimization where people have done that, but the gradient-based learning is really essential for neural networks. We'll see that for this also, of course, has a lot of influence on how you design your networks. You'll often think about like a design is only good if you have a good gradient flow. So you have to have the ability to learn good, so that you backpropagate your error, your gradients very well through the network. And so this is really essential by now, that you have a network which can fast learn, especially if you think about very deep networks, very many parameters. It's really important that you have some way of efficient learning of doing that, and that is currently best possible with like the backpropagation algorithm. So this already also invented in 1982 is core of all the deep learning models we have, and they only work that well because we can find these solutions by all the parameters efficiently optimizing towards a relative good solution. Then there is also, we see that more and more other type of network structures come. One is, for example, in 1989, the time-delayed neural networks, where we have a multi-layer perceptron, but which is no longer takes fixed input, but which can shift about things. Because in the world, a lot of things are not fixed. If you think about audio, there's not a fixed length audio. It's like a sequence. And you have to be able to deal with these types of different length sequence. And one way to do it is with time-delayed neural networks, nowadays called convolutional neural networks, which you can shift over your input and at each time step calculate your embeddings and recognize what patterns are in there. So this is shift invariant, meaning that if you recognize the same pattern at the beginning, at the end, or somewhere in between, which of course is often important to think about speech recognition, but also recognizing other phenomena in sequential data. It's really important that you can process different lengths audio, and it's not that important where it is. So then later in images, of course, there it's also important, whether it's an eye. It's not so important if it's on the top or on the bottom corner. An eye of a person can be everywhere, and therefore it's good to have these features which detect them. I mean, that is like the big difference to what we had before. So the standard feed-forward neural network, one important restriction is that you have a fixed size input and a fixed size output, which for several problems is fine, but for others is not. And then we have to look how we can do that different. I mean, this is more like a very subjective selection of some important steps. So in between there were others. We'll talk about RNN. But then really one essential one, which is very essential for current calculation, is then that people found out that you can use GPU to do deep learning. And you're just a lot more faster, because the one idea is you have to do a lot of repetitive calculations. We have seen the network architecture. You have to do the same perceptron at a lot of different positions. And that can be done very well with general purpose GPUs. And they were introduced 2007 and then applied in 2009 for applications of machine learning. And that is not to underestimate how important that is, only because we can do fast calculation. We can use a lot of data. And one interesting thing of machine learning and neural networks is they just get better the more data you have and the more parameters you have. I mean, not to everything, but in general, they get better. And so it's easy to improve your performance by have more data and have larger models, but that you can only do if you can do this calculation. So that just made that important, but it also later then influenced. So if we are talking about self-attention and transformer, we see that these are really dedicated and very well for GPU use case. So there you try to also develop then models which are just performing very well, or like which can be calculated very well there. And then like in the 2010 years, the success of deep learning happened in the different fields of AI. So for example, in vision, they have DenNet and AlexNet, where they successfully use deep learning models to win different competitions. So it's possible that you now have neural networks to really reach state of the art. And until then, often, I mean, we have seen a lot of success of neural networks. However, often with a lot of effort, specialized models were still performing often or giving the best performance. Since around that area, we see that starting from there in different areas, really successfully, you got the best performance in all these areas by applying some type of deep learning architecture. Then it also got successful, for example, in language processing. For that one essential component is the attention mechanism, which was introduced in 2015. Not yet for self-attention, but the general idea of attention, which makes it able to really summarize long inputs into a fixed size representation to use it then further. So it's also like one of these essential type of architectures, which we will look into and which enables the processing of very long type of data. One last important step is more not on the architecture side, but on the learning side step. More and more, again, we're successful using self-supervised learning to learn some type of hidden representations. I mean, the importance of hidden representations have been there before and analyzed. There has been used self-supervised learning in non-neural stuff with just language models, but really like combining the self-supervised learning with transfer learning made a large success and is a basic for foundation models. Initially, things like work-to-vec, but nowadays GPT and others, which are really where the nice thing is we can train the model on large data without having annotations. We can learn what is like a hidden structure in the input, and then it's a lot easier to learn task-specific things on limited amounts of data. And therefore, like when you look at current models, that you also partly train them at least in a self-supervised way is essential to get this type of performance. Again, because we want to have large models. In order to have large models, we need large amounts of data. And to process or like to train large amounts of data, it's impossible to collect them in a supervised way. So there, it's really important to also train them in a self-supervised way. Good. Then more before we are looking at the basics of neural networks, some more comments to how this AI or like neural networks interact with the general AI methods. But before we talk that, any more questions on the basics of or history of neural networks or questions? So feel free to ask. I mean, I guess today, hopefully, until now, it wasn't too complicated, but of course, if there's anything. So if you look at how people solve different types of AI problems, they are at least related. So this is a bit more focused on the on maybe natural language processing tools, but in general, it's a very similar scenario. So initially, people were mainly looking at rule-based systems. So you see, there was some learning in there, and there were some neural networks already. But if you look at big successful systems, at the beginning, they were often done rule-based. That means you really like describe rules, you more program your AI. So if you think about this function, you have to map some input to the output. You're not trying to learn it, but you're describing some rules and programming how to do that. So that can be done more on a vision-based model. If you have images they need to classify, you can look into what type of features you detect, what type of lines, and what is then. Or if you think about translation, there's maybe even more clear. There are strict rules. That is how you learn your second language in school. You learn that the vocabulary, like I translates to ich and like to liebe and so on. And this was exactly how you also did a lot of AI systems there. So there was no direct learning involved, which has, of course, also some nice things. So with this is explainable, perfectly explainable. So you can later look at which rules were applied. So it's clear why the system did this decision. So they have advantages. But they also have a lot of disadvantages. First of all, of course, that's very costly. You have to have a lot of experts writing you the code and writing you how to transform things. And secondly, the problem is the real world is not always that fixed. So there's very different types of inputs. And often, if you write a lot of rules, there's a new exception which you haven't thought of, and you cannot apply your rules. So that makes these types of rule-based AI systems, a bit limited. And that's why people looked into, instead of writing rules, can we also like learn how to do this transformation? So again, these arrows are mainly your function you want to learn. Instead of write rules how to do this function, you try to learn it by yourself. And there's like different steps in that. So initially, a lot of these were traditional statistical models. There's a lot of machine learning models which are out there, from HMMs to support vector machines and a lot of things, where you try to like count partial things, you design features describing your input, and then you have a model doing it. And it's the first one, which is corpus-based. So it's really like you're learning these things. It's no longer your hand rules. But typically, for each problem, you have an individual approach. So a lot of people looked into how can we do vision classification. Other people looked, how can we do machine translation? How can we do this and that? So each one has a very dedicated solution for this one. Then with the 2010 and with the hype of neural networks, we see that the one big advantage of neural networks is that we are no longer needing dedicated solutions, but this type of neural network seems to somehow work very well in a lot of different applications. And one main thing is that we are learning some type internal structures with a hidden representation. However, initially, we still have individual models. So you train one model to do image classification. You train one model for doing text classification and speech recognition and so on. What we are currently seeing is that this is even shifting in the area of large language models and foundation models. It's more and more coming that we are not having one model for each task, but we're having one model which can do a lot of different tasks. If you think about ChatGPT, it cannot only like answer you, it can do translation, it can tell you question answering, it can annotate your data. So there's a lot. If it's now added vision in there, it can do object recognition in images and so on. And the big advantage, of course, is if you not have dedicated models for each task, but you have one joint model, is that you're able to transfer your knowledge, which is important for students. You should not only learn directly what is like by heart, everything in the lecture, but you should be able to transfer that to new problems. A bit of that is also happening there. So if you learn in one task some aspect, you might be able to transfer it to another task and also apply it there. So how does this machine learning works? So we are always trying to learn this mapping. we typically have our training data where we have it annotated, and then we try to predict it on something else. And so one thing is here is, of course, in all of the machine learning and also all of the neural network, it's really essential that you think about a good data split. So you're not really interested in, if your model is very good to predict what you have already seen. If you have all your solutions, then it's not really important that the model is good to redo all the solutions. So if you're thinking of exams, exam is not there, and you shouldn't pass the exam by just doing all the old exams. You have to understand it, and you should be able to solve new solutions. That's why when training and working with neural networks, of course, it's important to split your data into your training data, where you train all your parameters, and then you have your evaluation and test data, where you check how good the performance is. Because, of course, your performance might be very good on your training data, but might be not as good here. And therefore, then, of course, that would be quite bad. Why do we need an additional data set? What we refer to as development data. Any idea already? I mean, yeah, we're doing machine learning, so everything should be learned. But to be honest, not everything typically is learned. In each of the models, you do a lot of your decisions. And I mean, if you think about a neural network, how many layers should you use? How big should your layers be? So there's a lot of parameters which you can decide on, and you cannot try all possibilities in there. You cannot easily optimize them because it's discrete parameters. You can't do gradient descent there. So we have to do a fix. And what you then do is normally you try a different ones. You try then on your development data, which one is your best hyperparameters, and then you do a final testing on here. Because if you train a lot of models and always test on the test data, at some point, you're not really, this is not longer unseen. So you have mainly, if you try a parameter one, length one, or like hidden dimension 1, 2, 3, 4, 5 till 1 million, and then you select the best one, it might be just that you'd select the best one for your test data, and you're not really like having an unseen test data anymore. So if you're doing your hyperparameter search, do it on your development data, and then do one final test on your test data. So that's so important, because with neural networks, we cannot normally prove model method 1 is better than method 2. What we normally do in proving it is we are running experiments, we are evaluating them, and if we are showing that it's better on some standard data sets, test sets, we assume, oh, this is a good idea, and you can publish it as your paper. But therefore, of course, it's important that you're not having like cheated in some way and seeing too often your test data. Good. So how are we doing the learning? And I already said that we'll cover a bit of different learnings. So therefore, it's good. Hopefully, you've heard about most of these different learning scenarios, and I will be therefore shortly repeat them here. So what we talked until now mainly about, and what will be also mainly covered in the lecture, is supervised learning. So the idea is that you have examples with your input and your output, and then you learn your function by just seeing all the examples and best approximating. So assume your task will be to do a model which predicts exam question grading. So you give exams with the answers from students, and you should predict what his grade is. So if you want to do this task, your input is a question and the answer pairs, and your label is how many points a human gave to that. And then you can train a model which tries to exactly do the same thing, but just learning from all the examples. Don't worry, we don't do that. But of course, it's an interesting problem. And the important thing is, you see, what your input data is and what your labels is really depends on the task. So for this task, input and question together is your input. While if you would build a model which does try to question answer, which tries to solve the exam, your input would be the question and the output would be the answer. So for this type of model, you would need to collect other data. Maybe it's nice because it might be easier to collect questions and answers than also to collect all the points. But if you want to build this type of model, you need this type of data. And that is a big challenge in supervised learning. Often this type of labeled data is limited. So you're not able to collect all possible of this data, but you have to somehow, deal with it in a way that that you can use as few data as you have, but also generate as much data as you can. Another important type of learning is unsupervised learning, for example, by clustering. We'll not cover that really significantly in this lecture, but just that you get the basic understanding. So the idea is that you, for example, if you again want to predict exam questions grading, you only have your question and answer pairs, and you don't have labels, so you don't know how many points it is. It still might be helpful to just train that and cluster them. And then if you grade one of them, you can hopefully see that all the others have the same grade. So that would be the advantage is it's easier to collect that data than to collect data which labels. But this is still helpful. Another way is combining these two things, and that is what we will cover in more detail, and that is referred to as self-supervised learning. So the idea is, okay, we have our task of grading exams where we have question and answers and the labels. Now we invent a new task where we only need our input data. So we only need the data which we have in the unsupervised case, but we are making it an artificial task. So that is here very easy. We can just predict the exam answers. So then the input for your model will be question and the output will be answer. So you're transferring your task now to a different task where you have a task with input and output, but you artificially created it from your purely input data, which was question answer pairs. So you don't need more data, but you can train a supervised model. So that's why it's self-supervised. On the one hand, it's unsupervised data, but you make out of it a supervised data set, and then you can train any of your supervised learning algorithms you have. And that still might be helpful. So for example, you can assume if you then can train an answerer, and then if you look how good how probable the answer is by the model, that might be a good indication of whether that is a correct answer or not. So of course, it's not that helpful, but it might be a first good starting point. The big advantage is, this is the big advantage if you have significantly more unsupervised data, non-labeled data, than you have labeled data in there. And there's also the in-between thing, so-called semi-supervised data, where you have grades only, for example, for some data. So you can do supervised learning there and do some type of unsupervised or self-supervised learning on the other data. Very realistic in a lot of real-world scenarios that you only have labeled data from part of the data, and you don't have labels for all the other data, but you still somehow need to process that. One last thing is reinforcement learning. We'll cover that only very briefly. There's a whole lecture on reinforcement learning at KIT, but the idea is there that you don't have correct answers for each of the individual tasks, but maybe only for all of the answers. So you only have the grade of the whole exams, but not for each question answer pair. Then you somehow have to learn that, if the grade is good, that means in average your answer should be also good. And if the grade is bad, in average these answers should be bad, but you can't for sure say that for each of them. So with this reward or later feedback, after all the exams questions, you then try to learn a model which also does that. Good. With this introduction to general AI methods, I will now, we want to have a more detailed look in the last 40 minutes on neural networks. But before doing that, any more questions to general learning. Okay, so for a neural network, as I said, the main idea is we have to predict some labels y, approximate them with our function. So all the thing the neural network has to do is to learn this function automatically and approximate. Of course, normally you can't exactly solve it. It's also that your data is not clean. Maybe there is no solution, or your model is too small to find the exact solution, but you're trying to do a best approximation as possible. There is, of course, other ways of doing that. There is naive Bayes classifiers, support vector machines, and other things. But as I said, the interesting thing is that currently for most tasks, just neural networks really work very, very well. And it's a standard thing to use. The basic thing of these neural networks are these perceptrons. And the nice thing is this is really very basic, very simple thing, which is using nothing else than things you have done in high school math. So main idea, you have an input vector x1 to xn. The important thing here is already it's a fixed size vector. So, and the basic neural network only accepts fixed size vectors. So you have to have some vector with n parameters. There is an x0. Often this is the bias. So you have this type of bias where this vector is always 1. So this input is always 1 to have a more better learning. And then you have your weights. That's W0 to Wn. You need exactly in the simple perceptron, you need exactly as many weights as you have inputs. And that is also why you can't have different types of inputs. Because if you now train a model with n weights, and now you get an input with n plus 1 inputs, which weight should you apply to it? That doesn't work. I mean, you always need the same number. So therefore, you then just do the weighted sum of them. So it's really just like x0 times w0, x1 times w1, x2 times w2, and so on. And that's your weighted sum. That is the result after your first step. Then you only have one additional step. That is the activation function, which typically nowadays is something like sigmoid or tangent hyperbolicus. We'll see why that needs to be the case soon. Originally, it was, for example, also the signum function. So if this is positive, then it's 1. If it's negative, it's minus 1 or so. That was in the original Rosenblatt. So you see, that is all the math you have in a normal perceptron. Not really difficult, but yeah, directly to compute. We also already heard, and we'll look into that now, it's not yet that powerful, but it's the core thing of still all neural networks that we have. You can also describe that differently. So you can, of course, describe that just as a formula. So your hidden activation or the sum is the sum of the WE and XIE, and then you do some activation function sigmoid, and that is your output. You can also do the more vector representation that is we'll see is especially common in with GPUs. So what this mainly means that you do the product of your weight vector times your input vector, that is k, and then you do an activation on that, and that's all that it does. So that is the basic thing. So just one vector multiplication and then some activation function. That is all that is happening in a perceptron. So not really something super fancy, very basic math, but by combining a lot of these very simple methods, we are able to do this performance. So what is really happening here? You can also do a graphical interpretation of that. And of course, for a graphical interpretation, it's only working really well if you have a two-dimensional input. If you have more than 2 dimensions, drawing gets difficult and so on. So assume you have an x which has 2 inputs, x1, x2, and you can then, of course, describe your x as your vector. So this could be one type of input that you're having. What you're then doing, we said previously, is you're multiplying this with your weight. So you have your weight vector. Again, it's also 2-dimensional. We said both have to be the same dimension. And what you're then doing is you're just taking the product of that. And so this is then here, this short vector. And that is the result. So this is a scalar that you have out of that. So you're taking your weight vector times your x vector. And this somehow very nicely shows if you now have then an activation function, it means that you're now checking whether this is positive or negative. If it's positive, your result is 1. If it's negative, your result is 0. So you can think about now what is the output of all your two-dimensional inputs here. And you nicely see then, if you think about that, and you have the activation function, positive is 1, negative is -1, that, for example, all the green area is then -1, and all the blue area is 1. Because if you do the scalar product on this orthogonal line, all the vectors have 0. So the product of all vectors on this line with W is 0. All of them which are on top is 1, and all of them which are below are 0. So if your point is somewhere here, you have a negative value. If your point is somewhere up there, you have a positive value. So you see very nicely what your model mainly does. With your weight, you control how you classify, and you always classify in these two blocks. So either it is positive or negative, and you can control that by your weight vector. You see now if you turn your weight vector, what you're mainly doing is you're turning your also then the other thing, which is orthogonal, and you're rotating it around, and then you can see what is the best type of classification in there. So that is what a basic perceptron in a 2D is doing. Any idea what we before said there is also a bias like the W0? What is that doing in addition in this graphical representation? Yeah. Yes, that's exactly it. So you're moving your boundary here from the original up and down. So currently here, your boundary always has to go through 0, 0 through the origin. You're just rotating on it. With a bias now, you can also move your thing up and down and adjust it. And with this one, you also see very nicely already what is a big restriction of that. So if you're doing this as a classification task, you only have the possibility to do a linear separation between the two classes. So you see that your separation between them is always in a 2D. It's just a line. So that's the only thing we can do. The decision boundary will be always this type of line. We cannot do any curves or anything. The only thing we can do is this fixed line, which we have to keep in there. And then there are very simple problems which can't be solved like this. In this case, if you have the XOR, you have the two blues, which are 1, and the two zeros, which are 0. And you see, you can now draw, the perceptron can only draw a line and will make all points on the one side positive and all points on the other side negative. And it doesn't really matter how you turn your line. You'll never be possible to put a line in this field so that all blue points are on the one side and all green points or purple points are on the other side. And therefore, that's why people refer to it as linear, so that it only has a linear separable function. So you always have to be this linear thing. And yeah, there's a lot of problems which can't be solved that easily. That's why just using one single perceptron is not really that powerful. There's all these problems which you can't solve because you always put just the single line in here and divide your space into the two classes. So what can we then do to make these things hopefully a bit better? And the thing is, it's really quite straightforward. So the only thing we have to do is not use one perceptron, but use a lot of perceptrons. So we can stack them on the Y, making the layers wider. Let's see the height. It's a bit turned, or making the network deeper, stacking more and more layers. then we have our input nodes, we have our hidden nodes, and we have our output nodes. And with this, we are then able to learn more complicated functions because we can now put a lot of different lines in there and define a very complicated space of that. So it's really the main idea is we are connecting all these perceptrons into this type of graph, which has a quite fixed structure. So we have the input nodes, then one hidden layer or several. A hidden layer is only connected to the previous layer, which can be the input or another hidden layer. And then the hidden layer is connected to the next layer, which can be the output layer or another layer. So you only have weights between them. And then you're always calculating in each of these nodes, you're calculating this weighted sum in there and then the activation function. So each of them is just a perceptron, and that's why this all together is called a multi-layer perceptron. So the calculation is quite similar. So again, the kj, now we are not having just one k, but several of them is like the weighted sum of the inputs. And of course, this time for each j, the weights depends on both. So there is the weights agree to the edges here, and they depend on both the input and the output. So you have the weights ji, which connect the input I with the hidden state j. So you still have a weight to a vector multiplication, and then you do your activation. Now you can also calculate all the things in one layer together. Then you, of course, can do that iteratively, but you can also just show that as a matrix vector multiplication. So you have the weights for each hidden state in one layer. That's why in the top row, you have for the first hidden state times x, and then you get the first hidden state up there, and so on. So you see that you can do your calculation by this vector or matrix vector multiplication. And you can calculate your full first hidden layer by just multiplying the weight matrix wji with your input, and then you get all your hidden states here. You apply again the activation function, and that's it. I hope I haven't lost you. So what are these activation functions? There's quite different ones. Most commonly used are mainly sigmoid, for example, tangent hyperbolicus, ReLU. You see, the important thing is they need to be not linear. So they have to do some nonlinearity in there. And we'll see later we have to do a decent gradient on that. So you should be able to calculate your gradient on all positions. And the gradient should be also not always zero, because with zero you can't learn. Why this is the case, we're seeing shortly. The first question is, why do we need this activation function? And that is very easy to see. So if we have now this two-layer neural network, what we are really doing is we are first multiplying our weight matrix with x, and then assume we don't have any activation function. Then in the next step, we are multiplying this result, which is k, with the weight matrix w, which is the second thing. So this is then just you're calculating your output O by multiplying two weight matrices to your input, assuming you don't have any activation function. Does anybody see a problem with this? Yes, exactly. So you can just multiply the matrices with themselves and before. And what we then have is just a single layer neural network again. And we saw that this is not really helpful because it only can solve linear separable problems. And therefore, in order to not make this possible, so that you can't do this type of shortening and summarizing these two matrices one, it's important to have in between your activation so that this is not the same and that you can learn more complex function. Because if you don't do the activation in between, then you can just summarize all your weights into one matrix, and in the end, you still have one single layer network without any hidden representation in there. Good. So this is for doing the calculation. Now the big challenge is, of course, how do we find the weights? So how do we train them? Because if you have the model, yeah, now you can maybe calculate your output, but this is not, yeah, is not easy to find good weights. If you especially think of current models, which millions or billions of parameters, you'll not be able to select them themselves. So the idea is to use some type of optimization algorithm to find them automatically. Yes. Yeah. I think it has to be nonlinear. Then it should be possible. So these normally the typical ones we use, you see there is a nonlinearity in there, and then that doesn't work in. I wouldn't assume so. I mean, maybe every linear, but I wouldn't be sure to prove it to you now. Mathematically wise, I think every nonlinear should definitely work. Maybe some other, I think, but yeah, I don't have the proof for that. This is just the things which work, which works. Yeah, what exactly are the properties? I have to check. I'm not completely sure. So how do we do the learning? And the thing is, we are doing supervised learning. So when we generate an output, we also have our targets. And what we are now trying to do is, okay, can we have some type of error metric which tells us how different our predictions are from the target? And if these predictions are very different, then we want to change our model. If it's very similar, we don't have to change the model. So the question is, how can we measure the error? And once we have the error, of course, how can we change the model that we get a lower error? So that is the important thing in neural networks, that we change the error in a way that we are reducing the error all the time, and there we're going in the right direction. There are different ways of measuring the error, typically things like mean square error, for example, where you just calculate the error for each thing. There's also this cross entropy, which is used especially in language. But in general, we'll have some function which measures the difference between our output and the target and tells us how good this is. And the target is then, or the training is then, can we find weights which minimizes this difference? And in order to minimize this difference, we can use then gradient descent. So calculating this error again is very easy. We just take the difference of the two vectors, we normalize it by 1 divided by n, and that's everything. So there's a lot of different error metrics. It really, of course, depends on your use case. All of them we'll see. Of course, again, you should be able to differentiate them again to calculate then the contribution and do that. With this, we can then do stochastic gradient descent. So what is the idea here? So as I said, the overall idea is we want to calculate the error, and then we change our weights in a way that we are minimizing the error. So you want to change your model to get better. It's like if you're writing in a test exam, you look at your errors, you're getting feedback, these are answers all wrong, then you have to change your model to now next time do the right answer. Exactly the same way we're doing. And the nice thing is we are not only telling this is wrong, but we can also tell the model, go into this direction, this is the right thing. How can we do that? So we have our error function. We don't know this function, of course. So for each weight, so we have one, if you have a look at one weight only, for each value of the weight, we're having an error. We could calculate the error. Of course, to do this, we would have to try all possible weights and then calculate the points in here, and we could find the optimum. But of course, that we can't do. But what we can do is, if we are currently at the point, at the purple point there, we can calculate our current error. But because we have a function where we can calculate the derivation, we can not only calculate the error itself, we can also calculate the derivation of the error. So if you think that of a graph, you know if the arrow gets bigger in that direction or if the arrow gets bigger in that direction. And with this information, we can then go into the direction where the arrow gets smaller. And that's what we're doing. And therefore, for each weight, we have a direction in which to go. We just don't have to go randomly, but we can also always do a directed search and go in this direction. And therefore, it's really essential that we always use their functions in our neural network where we can calculate the derivation, because then we can calculate our derivation of the error given the weight and go in the direction where we want to improve our system. And then we see the calculation itself is quite straightforward. We calculate the derivation. We can then go in this direction. So what means we update our weights by changing the weight a bit into the direction of the inverse direction of the gradient, and then do that. And then we can repeat that. We can also, of course, average the gradients and so on. But in the main idea is you not only know how big your current error is, you also know in which direction the error goes down, and then you're going in the direction of where the error goes down. Of course, there's one problem with this. Anybody see that in the graph? I think you could see it already. Yeah. Yes, and that's of course a big issue with this type of learning. We're only finding a local minimum. That's why there's a lot of tricks of how to try to prevent it. But of course, these are all heuristics. We can never be sure that we didn't find the global optimum. There's one thing which makes this even maybe more positive. Maybe it's even not best to get your global optimum, because this is a global optimum on your training data. So you're trying to find your global optimum on your training data. And typically, your global optimum on your training data might be some very specific case which works for your training data but doesn't generalize. That is a problem. I mean, you not really want to know this error function of your training data, but you want to know your error function of all your training data. And that you can, or all the data that you can't do, so approximate it by your training data, which already introduce the first type of noise in there. And the backpropagation is then, quite straightforward, and that we will look into now in the last quarter of an hour. So what you do is, and that's why it's calculate backpropagation, you first calculate your activation, you calculate your error, and then you're doing this backward step. For each weight in your network, you're calculating how big is the contribution of this weight to the overall error. And if this contribution is large, then you should change it largely in this direction. If the contribution is small, you don't have to change it then. So that's why then for each weight, you can go into the direction where it's getting better, and then hopefully get overall better. Again, you have, of course, a problem. If you change all your weights in parallel, it might be that because this weight goes in that direction, the other goes in a different, and you're getting even worse. But yeah, by averaging them and by doing it slowly, not making too much steps, this is the best type of heuristic you can do. But the big advantage, of course, is that you have a direction. You not have to guess and go somewhere, but there is some way which tells you this is a good way to go. Before we are looking at the example and doing that, all this backpropagation in one example, do you have any questions to this first? Good. So the nice thing about neural networks, again, is the math itself is quite simple. It's a quite easy network, and especially it's like a composition of very easy function. And we'll see with the chain rule that makes all the computation quite straightforward. So if you look at this very simple neural network with no hidden layer, so I know it's not perfect, but if I add no hidden layers here, things get complicated. Then what this function or how you calculate the error is quite straightforward. So what you do is you take your input. On your input, you apply your weighted sum. We call that K. On the input, you call your activation. That's then O. And then based on these final activations or outputs, you calculate your error. And that's all what your neural network is done. So what you're having do is you have a chain of different functions which are applied after each other. So first you apply the weighted sum, then you apply your activation function, and then on top you calculate your error. And that is your forward pass in there. And now you have to look at all the different functions we have there. And the nice thing, all these functions are really straightforward. So the weighted sum, we all know how to do that. It's the sum over all your inputs, the weighted sum times the input. And then you have here, for example, two weighted sums here. So how many hidden units you have there. Then you're doing afterwards, you're applying your sigmoid function. So, or any other activation function. So now you apply your activation function to K, and that's how you get O, the output of that. And once you have the output, you apply your error function. So you calculated, for example, the mean square error on that. So now with this, the question is how, I mean, then we have done our forward pass. We're up there. So the question is with this, how can we then do the, how can we calculate the derivation of that? So now what we need to do is, like, for each of the weights here, for example, we need to know how big is the contribution of this weights to the error up there. How we can do that is we have to take the derivation of our function, which is E and then O and K, derived to our weight WAJ. And what we can then nicely can apply, and that is the most important thing for the backpropagation, is we can apply the chain rule. Because what we can do is we can do the derivation of the error function to the output, then of the output to K, and then of K to WAJ. And each of them, we calculate the derivation. Each of them are quite simple functions. So calculating there, the derivation is possible. And then we can combine this to the overall derivation. So again, how we are doing that, we can do that step by step. So we have seen the weighted sum, the mean square error in this one. If you have a quadratic function, you calculate the derivation, you put the 2 in front, reduced by 1, and everything where not OI is 0, that's just constant. And only for, so you have your derivation is -2 divided by n, ye minus OE, and that's everything. So that's your derivation of the function E up there that you will later use. You only have to calculate this derivation. And as I said, this is like a derivation of just a quadratic function, which can be done. Then we have to do the activation function. I agree, this is a bit more complicated. If we have the sigmoid function, that is, for example, sigmoid from Ki times sigmoid from 1 minus Ki. I don't assume that you know that by heart, but all of these activation functions have defined derivations. And yeah, of course, these ones are not as easy to produce, but it's like 1 divided by 1 plus e to the power of minus x. I guess in higher maths, you have done something like that. But now we just assume this is the right derivation. What you now nicely see, hopefully, is it's important that you have an activation function which has a helpful derivation. Because if this would be 0, so for example, if you take the signum function, it's just 0 at all steps. Also at 0, it's not defined. Then you have here a 0, and your derivation will, as the product is in there, will always be 0. So therefore, it's important that you always take activation functions where you can calculate the derivation and where the derivation is meaningful in a way that you can use it for learning. And then you do the last thing. You have a weighted sum. There, your derivation is also quite straightforward. So the only thing you have to do is you do, if you derived the weighted sum to Wij, this is your variable. So then xj is just your derivation. It's a linear function in Wij, and that's all you have to do. with all these derivation, you can now put them into your chain rule, and you have your final derivation. So you can now calculate the contribution of this weights by these three terms. And you see how you do it by backwards. So you're calculating that for each layer, you have to store some information and backpropagate them. But then you see nicely how they fit in there. And you can do, even although it's overall maybe a more complex function, you see, because each part is quite simple, because you can apply the chain rule, you can calculate the contribution of each of these parts, yeah, quite well. You even need one more type of information typically. So what you also need is this type of derivation to xj. Any idea why we need that? So you see, this is mainly the same thing. The only difference is now we have the derivation not to the weight, but to xj. That's again very similar. You see nearly everything is the same except for a linear function. Now it's not xj, but wij. So yeah, quite similar. Why would we need that? Maybe not in this case, but in a little bit other cases, it's very, very helpful or very important. For exactly this, yeah? No, but I guess it's because I introduced this as the input. But if you now think about multi-layer, this is not really the input, but this is the hidden state of the previous layers. So if you stack more and more layers, now what you have to do is backpropagate your error even further. And then you have the error backpropagated to xj, and you can backpropagate it then from here further to the weights which are connected to this one. So this is needed to do the further backpropagation to the even lower layers. I mean, that's why I said it's not easy to get it, because I exactly said we have a simple network. But if this simple network is now part of a larger network where below x there is another hidden layer, then of course you have to backpropagate your error not only till this weights, but also to this weights and the weights lower than. And that can be done by propagating the error to the x, because then the x is the result of the weights and the inputs to this one. And so based on this error, you can backpropagate it then. Exactly as you have done there, the backpropagation based on the outputs, you then replace your outputs by your x and do it just more and more times. You see then how your error goes down, 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 all the way to the ground. And there you can then, even in a very large neural network, you can calculate the contribution of each of the errors to each of the weights that you have in there. Any more questions to the example? Good. So what did we do now? So we have now hopefully covered the basic of this multi-layer perceptron. So really, it's important to keep in the structure. So we have the input, then we have one or several layers of hidden layers, and then we have our output layers. They are connected. We only have connections between neighboring layers, and then we have this training process where we do the forward pass, we calculate the error. We then do the backward pass where we backpropagate the error to all the weights. Then we can update the weights with the rule we had before. And then you can train your weight, and you can always, then hopefully, I mean, you're not always improving, of course, because there's some randomness in that, but you're hopefully going roughly in the right direction. Good. So for today, what you hopefully remember is our organization, a bit about history, that there's a long time where there are people working on neural networks, and the basics, how a basic feed-forward neural network works. So with this, we will then look on Thursday how this is done on a GPU, and then we can look into more complex neural network structures in the next week. Thanks a lot.